So like I said, most of this is going to be review for you folks, starting with a review of basically the scientific method. Remember, science is just an organized way to gather evidence and learn about the world and the universe. And so in this class, we're going to be focusing more on the universe part of that. So science is always attempting to explain a real-world problem. Now, this can be a complex problem, like, are we alone in the universe? Or, it can be a more mundane thing, like, what plant is growing in my yard right now? Actually, a real question I'm looking into. Bought a house last summer. Things are coming up around a tree that I had cut down. I'm curious to find out if this is a plant that will survive now that it's in full sunlight. And we use the scientific method, which, again, the scientific method is really just a cycle of questioning, testing, gathering evidence. So you don't necessarily have to go in order of the scientific method. You can pretty much start at any point depending on kind of what you're dealing with. But a lot of times, the scientific method starts with observation. For example, me going out into my yard and going, I wonder what is sprouting here. It's green. It's coming up like little short shoots. That is my observation. Observation often leads to a hypothesis. So a hypothesis is a prediction based on something, okay? It is not, as many people say, a guess. A guess is random. I can ask you, what's the weather outside? Purple is a guess, okay? A hypothesis would be, well, it was sunny this morning, so I'm going to assume that, it's sunny or partly cloudy. Hypotheses are a prediction based on something that you know, or something that you think you know. They're not just a random guess. Once you have a hypothesis, then we need to test it. Now, the most ideal way to test any hypothesis is with a controlled experiment. A controlled experiment is the best way to do it. You're going to get the most conclusive results. And in a controlled experiment, you have an experimental group and a controlled group. So if you wanted to, let's say, test the effectiveness of different fertilizers on different plants, and you wanted to have a controlled experiment, well, you would make sure you add the same amount of fertilizer and the same amount of water to all your plants, but you would want to have an experimental group of plants that actually got fertilizer, and then you'd want a controlled group of plants that just got regular water so that you could have that comparison. And this is where we are testing our hypothesis here. The controlled experiment should help us be able to confirm or reject our hypothesis. And to do that, we need to collect the data, right? Obviously, if we were doing the fertilizer effectiveness test, right, we'd want to measure how much fertilizer we added, how much water. We want to measure the height of plants, maybe count how many leaves they have. All those kind of things that would indicate growth. Then you need to analyze the results, right? You would look at your measurements and go, okay, what do my measurements actually tell me? Do your measurements confirm your hypothesis, or do they not? And this will allow you to either accept the hypothesis acceptance, or if your data does not support the hypothesis, you will have to reject that hypothesis. And usually that leads to forming a new one and doing more testing. And as I said before, the scientific method doesn't always go in this order. Like, you can start at a lot of different points, depending on what you're doing. Also, for some types of science, you can't do controlled experiments, which is unfortunate. Controlled experiments are the gold standard. But sometimes there's too many variables to control for everything. For example, weather. When we want to know things like what causes tornadoes, you can't do a controlled experiment for that because there's simply too many variables to consider. Sometimes it's not ethical to do a controlled experiment. But if it's possible, controlled experiments are the gold standard. Are we ready to go on, or do we need a minute? Okay. All right. So the next thing I want to talk about is theories and laws. And this is an important thing to talk about because the way that we use these words in our everyday language, especially theory, is vastly different than how scientists use these words. That's what makes vocabulary in science tricky sometimes, is because the way we use the word in our everyday conversation is different than how scientists use it. A scientific theory is considered an accepted explanation of a phenomena that is supported with scientific evidence. However, theories, because they're explanations, theories can change over time as new evidence is discovered. A scientific law describes a mathematical relationship in nature. A lot of times when we use the word theory in our everyday language, we use it like the way scientists use hypothesis, right? Like a theory, isn't something necessarily that you have evidence for or that you know is true. But in science, a theory holds just as much weight as a law. They are both equally supported with evidence. The biggest difference between a scientific theory and a scientific law is that a theory explains a phenomenon. So a theory is an explanation of something. A law is a mathematical relationship. So typically a law is always going to have an equation associated with it. A lot of times, instead of even just using theory, a lot of times you'll hear me use the word model, because I think it's clearer than, theory because of the way we use theory in our everyday language. So kind of an examples for what this is. So let's talk about some examples of theories. So atomic theory, right? Like atoms existing. Obviously, no one thinks that, atoms are made up, right? Like, we know that atoms are there. And it's atomic theory. Atoms are a theory because it explains how matter forms and interacts with its surroundings. It's an explanation. And there's lots and lots of evidence that supports atomic theory. I've just listed a handful of experiments. If you've taken chemistry, some of them are probably familiar to you. The cathode ray experiment is how we know electrons exist. The gold foil experiment is how we know that there's a nucleus that has a positive charge. And with electron microscopes, now we can actually take images of atoms. So with electron microscopes, we know they're there because we can see them now. Another example of a theory is the theory of general relativity, that at some point we will probably talk about conceptually. We won't delve too deep into it because there's a little bit more math than all of us have the background for. But general relativity is a theory because it explains the phenomena of gravitation, or what we typically call gravity. And general relativity explains gravity as just an effect between masses and space-time. And we have lots and lots of evidence that supports general relativity. The lunar laser range finding experiment, which did confirm like some very specific distances and changing between it. Gravitational lensing, which we have observed in images, how black holes, their intense gravity can actually warp the image of stars around and galaxies around them. And gravitational waves were actually detected just a few years ago, which is another phenomena that is predicted by general relativity. So theories are supported with lots of evidence. We do know that they are true. Sometimes they change over time as we get new details, new evidence. But the main thing about a theory is that they explain how something happens. All right, are we ready for the next part? Okay. All right, so here's some examples of some laws, which if you've taken chemistry or physics, these ones are probably familiar to you. First off, Boyle's law. It describes a mathematical relationship between pressure and volume. They are inversely proportional to each other, which means if volume goes up, pressure goes down. If volume goes down, pressure goes up. There's an equation. You can graph it. Every single graph of pressure versus volume at a constant temperature will look like that picture. It's a mathematical relationship that we can use to make predictions about. Other example, Coulomb's law. Coulomb's law tells us how to figure out electric force. It gives us an equation because it describes the mathematical relationship between electric force, the amount of charge of two particles, and the distance between those two particles. But laws are always just mathematical relationships. You can graph them, you can get an equation from them. They're what we can do predictive calculations with. That's what makes laws so useful. Are we ready for the next part? Okay. All right. So now we're going to talk about claim, evidence, reasoning. So this may be a review for you guys, maybe not, but I would suspect probably, because I think most of you are upperclassmen. So claim, evidence, reasoning, it's just a framework that will help you construct a really good conclusion to an experiment or to like a scientific question. And so we break it into these three parts. The first part is a claim. Your claim is just a testable statement that answers the original question. Whatever the original question is, answer it in one sentence, that is your claim. The next section is always evidence. So you need to have evidence that supports the claim. So this is going to be scientific data from maybe an investigation or an experiment. Could be from just observations that you made about something, or it could be like from reading material or maybe like archived data. All of those would be good sources of evidence. The biggest thing to remember about evidence is that it needs to be appropriate and sufficient. Appropriate meaning it needs to be related to the claim. That's probably the obvious part. And sufficient meaning there has to be enough of it. So for this class, I would say you should always use at least 2 pieces of evidence to support the claim. And I think that is later in your notes. But we're going to always be using at least 2 pieces of evidence. Reasoning is kind of what takes your claim, takes your evidence, and ties it all together. The reasoning is going to show or explain why the data, the evidence that you chose, supports the claim. And your reasoning should tie in scientific principles or background information that is relevant to what is being talked about. So a lot of times for us, it's going to be, maybe a scientific theory or law that we've talked about, or even like a vocabulary term can be a good source of reasoning. And we're going to kind of walk through an example together, and that'll help probably clear this stuff up or review it for us. All right, are we ready to move on? Okay. So here's our example. Our question, are any of these liquids the same? Noticing we have 4 liquids. They're giving us the density of each, the color of each, the mass, and the melting point. So the first thing we have to do is make a claim. We'll go back to the bigger one. So our claim has to answer the question, right? So looking at this, do we think any of these liquids are the same? Okay, which ones do you think are the same? 1 and 4. Okay, why do we think maybe 1 and 4? Right, so the mass is the only thing that's different, right? Mass is going to depend on whether you've got like a big amount or a small amount, right? But things like density and color and melting point shouldn't be affected by whether you have a big or a small amount of something. But yeah, so liquid 1 and 4 both have a density of 0.93. They both have no color. They both have a melting point of negative 98 degrees Celsius. So for a claim, we could simply state liquid 1 and liquid 4 are the same. That's a good claim. It answers the original question. Your claim never has to be fancy. It can just be straightforward, to the point, one sentence. There you go. So the next thing we have to do is we have to pick evidence, which we kind of just did that when we figured out why we were going to pick those ones as our claim, right? We kind of said that, hey, densities are the same, the color's the same, the melting point's the same. Those would be our options for evidence, right? They both have a density of 0.93 grams per cubic centimeter. They both have no color, and they both have a melting point of negative 98 degrees Celsius. So now it comes to the reasoning, and this is kind of where we're tying it all together. So, and where we want to bring in some kind of like scientific principle, a vocab term, theory, law. And for this, like our main reasoning was, we said liquid 1 and 2 have the exact same properties. So they've got to be the same substance, right? Other than mass. But we know mass changes depending on whether you have a lot or a little bit of something. And if you wanted to work in like a specific law or vocab term, you know, the law of definite composition could work in here. Or just like the definition of a pure substance. You know, a pure substance has, you know, unique properties. That's what makes it a pure substance. Alrighty. So then, if we wanted to kind of put it all together in like a paragraph form, this is kind of how I did it for this one. Liquid 1 and liquid 4 are the same substance because they have the same intensive physical and chemical properties. Both liquid 1 and 4 have a density of 0.93 grams per cubic centimeters, a melting point of negative 98 degrees Celsius, and they both have no color. If two pure substances have identical physical intensive and chemical properties, they must be the same compound. Kind of the key things to point out here, when I mentioned the evidence in here, I was specific about it, okay? notice I said they have the same density, and then I listed the density. I listed the melting point. I described what the color was, okay? So if you want your evidence to be really good, you need to always make sure you specifically mention it. So don't just say they have the same density and the same melting point. Like, state what those numbers are. All right, now we'll do kind of an example here as a class. So our example says, Sammy wants to see if plants grow better in sunlight. He uses 3 plants of the same type and size in 3 locations. Plant A is in the center of the room. Plant B is placed inside a closet. Plant C is placed near a window. After 5 days, Sammy measures the growth of each plant and records it in the table below. So here's kind of the things that we want to make a note from the explanation, right? So plant A was by the window, so we know it's going to get the most light.
No, wait, plant A was placed in the center of the room.
Oh, it was in the center of the room. Which one was by the window?
That was C.
C. Okay, so C got the most light. And then B was in the closet, right?
Yes.
So that was the least amount of light. And then we know plant A is going to be in the middle. And if we kind of look at the data here, right, plant A started at 12 centimeters, went to 14. So it grew 2 centimeters. Plant B started at 12, went to 13, so it only grew 1 centimeter. Plant C went from 12 centimeters to 16, so it grew 4 centimeters. So based on this data here, what kind of a claim could we make? Knowing that our question was, does sunlight make plants grow better? Right? Yes. Yes, sunlight makes plants grow better. The claim does not have to be deep or like flowery. It can just be straightforward to the point. We are seeing in our evidence here, sunlight makes plants grow better. You could have also said something like, you know, the more sunlight, the more a plant grows, or the plants that receive more sunlight make them grow the most. Yeah.
But some plants work better in shade, grow more shade. So it's like, does it work if you say it like the same?
Well, I mean, you would not be able to extrapolate this to any other plants than what was tested in this particular situation. But yeah, you're absolutely right. Like if you did this experiment with a different type of plant, you might get different results.
Yeah, you just said like Sammy wants to see if plants grow better.
Right, it's not the most sophisticated designed experiment.
Right.
Obviously, it should be more detailed. I just picked a simple example off the internet. Okay, so now we've got our claim. Now we've got to pick some evidence. So what would we want to use as evidence?
Just say plant C that had the most sunlight grew 3 more centimeters in the same amount of time as plant B with less sunlight.
Okay, so we want to highlight C and B, right? That got the least and most sunlight. And if we talk about both of those, then that's our 2 pieces of evidence, right? So we said plant C received the most sunlight and grew 3 centimeters more than plant B. That received the least sunlight. Okay, so for our evidence, we have plant C received the most sunlight and grew 3 centimeters more than plant B that received the least sunlight. We mentioned both plants. Plant B and C were the best ones to use because they were our extrema, our most light and least light. And we mentioned the difference in growth. So the very last thing that we would need to do here is we'd need our reasoning to kind of tie it all up, which a lot of times we can kind of restate the claim a little bit in that. And we also want to tie in some kind of scientific principle, so like a vocab term, a theory, or a law that supports our claim and our data. So is there some kind of theory, law, phenomenon that we maybe remember from a previous science class that could go along with supporting this? What is something that we remember about science that would support the data that sunlight is making the plants grow more? Anything from biology? I know it might have been a minute since some of you had biology. Yeah.
Photosynthesis?
Yes, photosynthesis, right? Photosynthesis is the process by how plants, take carbon dioxide and water and turn it into sugar to grow. It's how plants make energy, basically, to grow, and that requires sunlight. Therefore, the more sunlight a plant receives, the better it grows. So we could say plants, no, I don't like how that color turns out. Okay. Plants make energy, it's the simplified version, by photosynthesis, which requires sunlight, period. Therefore, the more sunlight a plant gets, the more it will grow. So our reasoning, plants make energy by photosynthesis, which requires sunlight. Therefore, the more sunlight a plant gets, the more it will grow. Again, a very simplified example here, but you can see how we can take data that was given to us. We can make a simple claim, use evidence, the actual data to support that claim, and then we can work in a reasoning. And we'll probably be doing a handful of these throughout the trimester related to different things that we'll be doing.